again, welcome back to the latest lecture session. A quick recap of what we have been up to. We have been discussing how to remediate contaminated groundwater. We looked at containment, pump and treat, and very briefly discussed source control, right? And looked at the relevant aspects there. And then we very briefly touched upon a relevant option called permeable reactive barriers, right? So let's dig further. So what do we have here? We have permeable reactive barriers. The key is that though we term them barriers, right, they are permeable and reactive, right? In the context that you want to see to it or facilitate the relevant groundwater to flow through this particular barrier that you are going to construct subsurface or beneath the surface, right? And you are going to have reactive media or the relevant reactive media in that particular barrier, right? So that you will have either the removal or degradation of the relevant contaminant. So let's look at the relevant aspects here. So again, to make it clear or to help you visualize, let's say here we have the side view. So you have the contaminated waste, let's say, think of this as a landfill, let's say, and let's say the liner or the leachate collection system failed, and now you have the leachate, coming through and then permeating through and reaching the groundwater and then being transported over a considerable area, let's say, or a considerable extent now, let's say. Now, what's the PRB here? Where is the PRB here? Here I am going to have the PRB here. This is obviously the side view, right? And as the groundwater flows through this particular barrier or reactive media, you are going to have the relevant reactions out here, and the water coming out is going to be the treated water here, right? So again, this is your PRB out here. So the key aspects are that you are going to have it constructed subsurface, obviously, and perpendicular to the groundwater flow, right? And again, the relevant porosity of the relevant barrier is going to be relatively less than the relevant surrounding media. Why is that? Obviously, you want the water to flow through the barrier, and obviously if you have the porosity greater than the relevant porosity of the media, the water is going to take the path of least resistance and flow around the barrier, right? So again, this is the relevant aspect. So obviously there are many technical aspects relevant here. We'll look at those aspects later, but let's look at some of the general pieces of information here, right? So one way obviously here is to treat the groundwater, and the other way is, let's say, if you identified the spill relatively early, you can have this kind of a mechanism to treat the relevant leachate that's coming through, or the spill that's permeating through before it reaches the groundwater, right? Again, just two different cases. So again, different view here. So here is my contaminated zone, and I have groundwater flowing through, right? And obviously here, and now as you can see here, the thickness, this is the thickness of the relevant PRB, but aspects to be considered carefully are the length and the width or the height of the relevant PRB, right? Because if you do not estimate your contaminated plume accurately, as in this is my contaminated plume, let's say, right, accurately, and if I do not obviously place or calculate the relevant length and height of the PRB, I am obviously going to miss the plume, let's say, and the plume can flow around the relevant PRB. So these are aspects that need to be considered. Again, we'll look at those in greater detail later on, right? Again, relevant reactions occurring within this particular PRB, and then you have the treated contaminant coming out of the PRB, right? And here typically obviously I did mention that PRB is widely used. As you can see here, we are looking at field installations either for full scale or pilot scale for volatile organic carbon, right? Typically in industrialized nations, let's say, or industrial areas, you have contamination of the soil and groundwater by volatile organic carbons, right? Or volatile organic compounds, right? And they are typically toxic, let's say, hydrophobic, right? And the key here is that they are hydrophobic, right? So as you know, pump and treat, not really a good way to address groundwater contaminated with hydrophobic compound, right? So in that context, obviously the PRBs are going to be remarkably worthwhile, or are going to facilitate the remediation greatly. Let's look at why later on. As you can see, typically the east coast of the US relatively more industrialized, and you see many installations there, and again western coast, California and such. Again, if you take European Union or such, typically this is the picture you see, that there are many PRBs installed out there. Again, as I mentioned, in the Indian context, not many, or to my knowledge none, I guess, right? But again, that's because of lack of transfer of knowledge, and maybe the complexities inherent in the Indian context, or the type of soil in the Indian context, I guess, right? So again, obviously if we know what are the options, you can obviously choose whether the relevant option is worthwhile or suitable to you or not, right? So again, we'll move on. So here there are two types of PRB configurations. So one is the continuous, one is the funnel end gate. Continuous as in I have the reactive media throughout the relevant PRB, and the width of this particular PRB is greater than the width of this particular contaminated plume, right? So continuous PRB now. So funnel gate, obviously as the name indicates, and as you can see here, you have only a part of this particular system to contain the containing the reactive media, and then you have impermeable, let's say, gates, if I can call them, right, that would channel the groundwater towards this particular reactive and permeable zone, right. So two cases, what is it now, the continuous PRB and the funnel end gate system. But typically with the funnel end gate though, you will obviously need to be able to very accurately estimate the plume shape and size, right. So typically I believe most people try to go for the continuous PRB though, right. So as in even if there is a change in the shape of the particular contaminated plume, this particular continuous PRB can address the relevant issues, right. So I'll move on. So again here I have the top view with respect to funnel end gate, right. So plume coming in, let's say, and then being channeled towards my particular reactive media, and then I have the remediated groundwater after the relevant reactions within my particular reactive medium, right. And also obviously here we have what we say multiple gates, let's say I have multiple gates or multiple zones. Yes, again depending upon the site conditions, let's say you can have multiple such particular cases. So again, even within funnel and gate, keep in mind that we can have different gates out here. Yes, so the PRB again installation, where do I install the PRB now, right. So obviously two aspects need to be considered. If I know the shape of the relevant plume and its distribution pretty accurately, or I am relatively more confident based upon my monitoring network out there, I can try to address the issue at the source, right. I can try to address the issue at the source by installing the PRB so that it catches the contaminated groundwater plume, right. But let's say that's not the case, and maybe the extent is too huge, let's say the extent of contaminant is too huge, and what do I do in that case though, let's say. Then I can install the PRB near the receptor locations, as in let's say I have a village out there and I know the locations from where they are, let's say drawing the water or withdrawing the water. So I can try to look at the particular location where let's say the installation of PRB would see to it that only the treated groundwater would reach the relevant extraction locations for that particular village, right. So here again, as we talked about, one aspect with respect to source control orientation. So you have the plume here, and the PRB tries to capture that particular source, and the well field is out here. But let's say the second aspect is the receptor protection orientation. I have the contaminated source here, I have the plume here, right. But here the key aspect is that I am trying to protect the relevant withdrawal sources, let's say, for the relevant receptor, right. So two aspects. Moving on, again different kinds and different ways of constructing PRBs. Typically constructing the PRB is maybe in the Indian context a challenge, because I guess we haven't, or we don't have much experience, but it should not be complex, because our construction or the relevant companies are remarkably competent, I would say, in various fields, and thus should not be an issue. But again, keep in mind we have different kinds, let's say powdered, I think here we have fine grained, and in B coarse grained is being laid in a trench. So this is the trench, I believe continuous PRB, and they are placing the coarse grained zero valent iron. NZVI is the zero valent iron that's being placed here in this continuous trench here, right. And third one is micro scale zero valent iron in a slurry. This is a slurry that's going to be injected here, right. And again installation, different methods of installation here, right. So let's move on again. Application, I guess, in which particular cases or context would this be more applicable now, right. So think of this now, the key aspects are that it's subsurface, let's say, and there is no active maintenance or such required, right, other than monitoring the plume before and after. So the key aspect obviously is that here you can treat the volatile organic carbons, let's say, or those hydrophobic compounds or NaPl, which you cannot buy pump and treat, let's say, right. Again, there are different applications for PRB depending upon your site conditions, but obviously one particular aspect that comes to mind is because is the NaPl or the VOCs, because we just looked at or discussed those aspects in the previous couple of sessions, right. So obviously what was the case earlier? So you had the relevant compound adsorbed onto the soil, right, adsorbed onto the soil or present as NaPl. So even though you pumped out the groundwater and treated that groundwater, you again have release of the contaminant from the soil or from the NaPl into the groundwater, again contamination, right. So obviously this active mechanism of trying to pump the water out and treat it, was failing in that context. We looked at the relevant numbers too. So here this particular case, PRB, obviously a passive technique, right. So I have the PRB in place. So as and when the relevant contaminant from the relevant soil or NaPl is released into the groundwater and groundwater comes in contact with the PRB, it's going to be treated, right. So that's one particular case obviously where it's greatly applicable. So let's look at some of the other aspects here. So when my location is not clear, let's say, or the location of the source, pardon me, is not clear, that's one particular aspect. And obviously slow contaminant release from the source, right, and this again leads to tailing and rebound. Different cases, stratification, NaPl, adsorption, so on and so forth. And then let's say if the contaminant is again relatively less soluble, let's say, right. Again for hydrophobic compounds, let's say typically solubility is relatively less, but high enough such that it's above the regulatory standards, right. So in that context, what do you have? I'm going to have or end up observing this tailing and rebound, right. And obviously if the contaminated soil is, volume of contaminated soil is way too high and it's not feasible to have either ex situ or in situ treatment of the relevant soil, let's say, what can I go for? I can have this passive technique, as in I place these PRBs at strategic locations, capture the plume, and then let the PRB do its job now, right. So and moving on, and this is an aspect that's remarkably relevant in the Indian context. So let's say I think we looked at case of Ghaziabad, let's say, where obviously they were looking at pump and treat and also by putting in engineered microbes, I believe, let's say, if not engineered microbes, non-native species into that particular case or remediated site to reduce chromium from 6 to 3 and so on and remediate the site. So again, the key aspect there is now they had to occupy a whole park, let's say, whole as in, I guess, a huge park, right, and that particular location, which Ghaziabad, again, keep in mind the land area, again the costs are remarkably high, let's say, population density is high, and again keep in mind also the relevant park is being deprived of its natural, or the people are deprived of usage of that particular park, right. So here, at least in the Indian context where you have built up areas, let's say, and land is a precious source or resource, pardon me, having PRBs is, let's say, is going to be remarkably worthwhile, or an option that certainly should be considered, let's say. Why is that? As you see at subsurface, the footprint, let's say, is going to be remarkably less. You just need a couple of monitoring wells, let's say, at the strategic locations, right. But obviously you need to be able to understand the relevant plume size and distribution accurately, right. So again, these are the aspects. Again, we did look at this particular case earlier, tailing and rebound. As we know, theoretical case would be this, as in if it's only in the dissolved phase, I'll be done with removing the contaminant when I pump out that contaminant plume. So that's why I see that the concentration of the compound that's being pumped out relatively constant, and once all the plume is, let's say, pumped out, a sharp fall, and then what would you expect? Nothing out there. But for slow contaminant release, hydrophobic compounds, NaPl desorption or adsorption onto soil and so on, you will have tailing. Again, what does that do? Increase the time required, and also rebound, which makes it impractical for most pump and treat options, right. In this case, obviously the PRBs are a pretty good option now, right. So moving on, so what are the advantages of PRBs, right. So let's look at some of these aspects. So treatment occurs subsurface, that's something we looked at, because let's say if you have considerable built up area, right, and if the land costs are relatively high, again that's going to be remarkably worthwhile in that context. Treatment occurs in the subsurface. Again, operation and maintenance costs are relatively low or remarkably low because it's a passive techniques. and again no above ground structures are required and no labor costs or such, right. And then again most of these aspects relate to what do we say, the use of that particular built up area now, right. Full economic use of a property, and again as I mentioned earlier, the treatment is passive, right. Again coming back to the lower, passive more or less relates to lower operation and maintenance costs, yes. And the key here is that unlike other particular techniques, let us say pump and treat, containment or such, right, you need to obviously monitor the relevant plume, right. But in this context, let us say of permeable reactive barriers, you will need to only look at, let us say, a few areas that need to be, or few locations that need to be monitored. For pump and treat, let us say you need to have wider monitoring network, let us say, right, or for natural attenuation, let us say, or so you need to have wider monitoring network. But for PRB, let us say I need to have, what do we say, typically what do we say, the monitoring wells or locations before and after the PRB, and let us say inside the PRB and beside the PRB, right. Beside because I want to see if the plume is escaping the PRB, before and after to look at the performance, inside too obviously for the same reason, right. So here again the costs are going to be relatively less, yes. So moving on, the key aspect is that as I mentioned earlier, you know, it can be used in conjunction with other alternatives now, right. So here let us say we have a particular graph here. So here we have the plume traveling with distance here, let us say this is distance on the x axis, and on the y axis I have this trichloroethylene, let us say here, right, TCE here at this particular concentration. Obviously you know it is going to decrease because of advection and diffusion, you are going to have dilution of the relevant compound, and so if I take the sample along the center line I am going to see a decrease, and also natural attenuation as in if the microbes have the relevant electron donor here, or I think yeah it is a donor here, right, you know that should serve the purpose, right. Again you will see some decrease maybe, but not at the rate that you want to, and here is the target concentration, and maybe here you have, let us say, the source of different wells. So that is why I have that as compliance point. So from here let us say your village withdraws water, and so by here or by this location I need to go beyond this or below this particular standard or regulatory limit, let us say, right. So what can I do? Let us say I know that natural attenuation does take place, but it is not fast enough to be able to meet the relevant standard. So what can I do? I can design the PRB here, let us say, right, and at this particular distance, and that as the groundwater comes in and it moves out, it is going to be decreased to a particular value depending obviously upon your thickness. So here again we have the PRB, and that is going to you know, let us say act in conjunction with natural degradation or natural attenuation, right. So typically you have, what do we say, the microbes doing their job, you know, as they do out there in nature. They you know obviously look for sources of what do we say, energy in the terms of electron acceptors and donors, right. Again that is something we are going to discuss later, but let us say that is not good enough to do the job. Let us say what can I do? I can augment this particular natural attenuation by, you know, putting in a PRB. So as you see here, you know, the influent water at this particular point or in this distance is at a relatively high concentration. After the PRB again it comes down to the relevant design value, let us say, and how do I come up with this design basis? Estimating that, you know, natural attenuation let us say takes place at a considerable rate, not considerable, at a certain rate, I can you know, try to look at the design value which would allow the microbes to do their own job, and by the time, not time, pardon me, by the time, not say the distance, let us say after traveling a certain distance and the plume reaches the relevant receptor, you know, the relevant concentration is below the relevant standards, right. So again that is something we can look at. And again, what are the treatment mechanisms, right? Is it only redox process, is it only sorption, or in which case is this applicable, and so on and so forth. Let us look at that. Obviously one widely used treatment mechanism is the redox process, oxidation and reduction. So what are these oxidation and reduction, what do we say, reactions about now, right? Well, they are discussed, I am sure, widely, right, but a quick recap should you know, help those people who have relatively less background in this regard. Let us see. Redox reactions typically deal with what we say, the transfer of electrons, right. So typically I think we looked at this C2HCl3, I think TCE, right, trichloroethylene, right. So as you see here, this is an oxidized compound, right. I mean you can try to look at or try to calculate the oxidation state of carbon here, but again as I know that we have Cl here, let us say, and typically from that we can understand that this is an oxidized compound now. and typically the presence of this Cl imparts the toxicity to your particular compound here. So what do I want to do? I want to remove that Cl now. How is that going to happen? Again, through what we say reducing this particular compound. As in, this is an oxidized compound, so I need to reduce it, or I need to provide a source of electrons, right? So this compound is an electron acceptor, right? So I need to provide an electron donor. So once I provide that, let's say, and if this is my contaminant in the groundwater and I provide an electron donor, typically let's say, as we saw earlier, zero valent iron widely used, right? Zero valent iron is a reducing agent, it provides the relevant electrons, right? We are going to again look at these aspects later on. So I need to provide an electron donor, right? So again, why is that required? Obviously because this compound is an electron acceptor, TCE, and once I provide the relevant electron donor, the redox reaction is going to take place, and you are going to have reductive dechlorination of the relevant compound, and thus let's say, the toxicity is going to decrease depending upon the pathway anyway, right? So what are the other aspects again? So acid base reactions again typically used for pH control. Let's say you have acid mine drainage, and there let's say the relevant pH is an issue, let's say, right? Again, you can have these subsurface systems. There are again other treatment techniques for acid mine drainage, but you can have pH control by PRB. So depending upon, let's say, if you want to increase the pH or lower the pH, but typically in acid mine drainage you typically want to increase the pH, you can have the relevant media to be limestone or such, right? So again, we'll move on. Chemical precipitation. So here let's say I'm treating the compound or degrading the compound typically in redox process, and it can also lead to precipitation of the relevant degraded product or byproduct. Acid base reactions, exchange of H plus, or typically H plus is involved here, right? And chemical precipitation, right? So again, in the case of Ghaziabad 2, what did we look at? Let's say the example that we have been referring to considerably. So they were trying to change the oxidation state from chromium 6 to chromium 3, right? Chromium 6 remarkably toxic, chromium 3 slightly toxic or relatively less toxic, but the key aspect is chromium 3 is insoluble, right? So insoluble in the sense that the concentrations, the equilibrium concentrations or the solubility gives you an idea about the maximum concentration at equilibrium, let's say, the solution can have, let's say, right? So if the solution or the compound is relatively insoluble, what does that mean? The compound would precipitate out, right? So again, you can have reactive media that would help facilitate this particular chemical precipitation of the contaminant, right? And then adsorption reactions, as in you can have compound, let's say, that can act as a site for this particular contaminant to be adsorbed onto, right? So typically these are the four major chemical or physiochemical process. And then you can also have media that would promote, let's say, the biological process. Yes, you want to attenuate, let's say, or try to increase the effectiveness of the biological process. For that, again, you can provide the relevant electron acceptor or donor again, right? So we are going to discuss oxidation-reduction reactions in relatively greater detail, and typically we come across the zero valent iron in the context of PRBs now, right? Most of the relevant compounds, typically, let's say, the organic solvents, let's say, or the volatile organic compounds are typically oxidized, and you want to reduce them. So in that context, we place zero valent iron, and typically what do we have? The process involved are redox process, right? So let's look at what we have here. So this is zero valent iron, right? Zero valent iron, and what can that transform into, let's say? So it can, it's an electron donor, as I mentioned earlier, or it's a reducing agent, right? It's a reducing agent, electron donor. So it's donating the electrons, and now you have Fe2 plus here, right? Ferrous iron. Or, okay, there is another case that I want to look at, but we'll come back to that later. So these electrons that were released by or donated by Fe0 or the zero valent iron can then be accepted by this TCE, right? And also change in pH, I guess, and then you can have the relevant degradation to more simpler compounds, C2H4. So here it's more oxidized, and here, as you can see, it's reduced form, right? And here you see that the Cl minus is released, and typically this particular compound is either can be further degraded, let's say, if you want to, or you can let the microbes do their own do their job, right? So again, what do we have here? We have an exchange of electrons. So zero valent iron is the electron donor, and the relevant contaminant, which is the TCE here, is the electron acceptor, and in that process it leads to degradation of the relevant compound here, right. And here let us say this is the what do we say, these are the half reactions, right, and this is obviously the relevant reaction. So obviously you see that the pH, or H plus is going to be taken up, so the pH will increase. So that again needs to be considered in that particular system, obviously, right. So moving on, so reductive precipitation of hexavalent chromium, this is the example that I was referring to earlier. So I have CrO4 2 minus, oxidation state is +6 here for chromium, right. How do I calculate the oxidation state of chromium here? So if I assume that the oxidation state of chromium is X plus 4 times oxidation state of oxygen, typically -2, is equal to -2, and solve for X, I see that it is +6 here, right. And here again I have 0 valent iron, right, as I know that from here it is an electron donor, so it is providing the relevant electrons, right. And then again in the presence of, or it takes in H plus, let us say it is oxidized, or Fe naught is oxidized to Fe3 plus, but CrO4 2 minus is reduced to Ce3 plus. How can I say it is reduced? Earlier the oxidation state of chromium was +6, and here as I can see the oxidation state is +3, right. So it has taken in 3 electrons, let us say, as you can see here, right. So +6 to +3, and here as I know, or we mentioned earlier, Cr3 plus is again relatively insoluble, and you are going to have the relevant precipitation, right. So again why is this particular background relevant now? Because obviously only if you have an idea about, let us say, the relevant compound and its relevant chemistry, can you design the relevant reactive barrier, let us say, and also you also need to look at which media to obviously put in, right. So these are the aspects you need to be aware of, and I guess here I have the relevant equation here, right. Cr3 plus 1 minus X Fe3 plus and so on, the generic equation anyway, right. Again you have complex of iron and chromium being formed, and again are the precipitate, I guess, right. Again different ways. So here is the reduction from Cr +6 or chromium +6 to +3, and here you see the precipitation, I guess, right. That is why we call it the reductive precipitation of hexavalent chromium, yes. Okay, moving on, we looked at reduction, and typically sorption and precipitation of redox tends to oxyanions. Let us look at some of them. So selenium 6 looks like is more soluble than selenium 4. So what do I want to do or promote? Let us say sorb down to iron oxyhydroxide surfaces, right, and uranium treatment by elemental iron, let us say, and what is the process? Again it is not clear, but looks like it is reductive precipitation, and also let us say, or could be sorption onto hydrospheric oxide. Let us say when you have iron, let us say, and let us say you have, what do we say, it being oxidized, let us say, right, you are going to again have formation of the relevant oxides here, right. You are going to have complexes being formed, or relevant, what do we say, precipitate of that particular ferric or such, let us say, right. And again you are going to have now sites for adsorption of the relevant compound, and so here it can either be reductive precipitation of this particular uranium, or sorption of uranium onto the hydrous ferric oxides, or co-precipitation along with the iron oxides, as I mentioned, as in this Fe2 plus is oxidized to Fe3 plus, and as that precipitates, that provides site for your particular contaminant to again precipitate upon or adsorb upon, and that is typically referred to as co-precipitation, right. So I believe I have one particular data set here, and here we have time on the x-axis, and here we are looking at uranium removal, and the key aspect is that its 0 valent iron PRB was used in Utah, I guess, right. And here we have on y-axis the relevant concentration, let us see, that is the higher the data here, obviously, as you can see from this particular metric, the better. So let us say they are measuring at 0.15 meters or 15 centimeters into the PRB. Typically the PRBs are not many meters thick, let us say, typically less than a meter thick, yes, and as you can see here the efficiency increased, and then it held well for considerable period of time, and again the relevant mechanisms could be any of these 3 mechanisms, either reductive precipitation, sorption, or co-precipitation, right. Again this is from what we say real life scenario in Utah, I guess, right. Okay, and next aspect, so again we looked at sorption mechanism. Let us look at try to understand these aspects here. So, three cases we are going to look at here: sorption only, sorption and reduction only, right. So, again as I mentioned here, iron, let us say, can act as an reducing agent. Iron as in zero valent iron can act as a reducing agent, right. Either it can donate 2 electrons and be oxidized to Fe2 plus, or more further what do we say, oxidation to Fe3 plus and donate 1 further electron, right. Or it can also, what do we say, lead to reduction and sorption, in the sense that Fe3 plus, let us say, can precipitate out or will precipitate out depending upon the concentrations, and then that can act as site for co-precipitation or adsorption, let us say. So, that is a case where we see sorption and reduction, or depending upon, let us say, if the compound cannot be reduced by the relevant Fe2 plus or zero valent iron, it can just act as site for adsorption. So, let us look at some of these aspects obviously. So, here we have the E naught. I guess we will look at this in greater detail in the next class, because we are almost out of time, right. So, here depending upon the E naught value, let us say, you can understand, let us say, well, Fe2 plus zero valent iron, while being transformed into Fe2 plus and or Fe3 plus, be able to reduce the compound or not. We are going to look at some background about that in the next class. Again, in the same cases, I have what we say copper, mercury, and so on and so forth, which can be reduced by iron, right. And so, these are the different ways or mechanisms by which zero valent iron, the most widely used reactive media for PRB, let us say, can lead to removal or degradation of your relevant contaminant, right. So, again what is it typically now? Redox process, redox and precipitation or adsorption, right. So, again we are going to continue this in looking at the relevant technical aspects in greater detail from the next session, right. And for today that is it from me, and thank you.